Okay, welcome everyone to this continuation of what is tropical geometry. We are already at part 12 of tropical geometry, and I guess it's time to look into, well, the more abstract part of tropical geometry. I don't know, the more definition type part of tropical geometry. So we start to get going with what a real textbook would do, right? If you're not watching YouTube, but you're instead of reading a textbook, you probably will start with something like evaluation, which doesn't look very tropical on first sight, but it's actually very tropical, as we will see. Yeah, so let's have a look at valuations, which is what you use in tropical geometry, because we'll see why. Bear with me. So I think the whole idea of valuations doesn't quite come from how I would do it, or how I would explain it, how I will explain it, but it comes from something different that I mentioned later, but this one was around before, and come back to that later. So right now I'm just looking at poles and zeros of a function, and funnily, it's actually very funny, I think there is a Wikipedia page which is just called zeros and poles, I think, the other way around. Zeros and poles. I was pretty sure that there you go. Zeros and poles. I was pretty sure that there was a Wikipedia page just called zeros and poles, indicating how important zeros and poles are, or poles and zeros, whatever. So they're essentially opposite of one another. So a zero of f is a pole of f inverse, and the pole of f inverse is a zero of f. So they're really just doing kind of the inverse of one another, right? So a pole is what you see here. Here's a pole, here's a pole, here's a pole, here's a pole, here's a pole. Yeah. Essentially, a pole is where you divide by 0. So we have a function f, and dividing by 0, that's a pole. And fine, all good. Of course, these are interesting parts of a polynomial or whatever a rational function, like the zeros are, right? Kind of really, these are just the inverse of them. But maybe we want to be a little bit more sophisticated, and we want to measure how often one divides by 0. Yeah. So I have a nice plot on the next one. Let's just open Desmos. Can I spell? So kind of, I'm a big fan at this point because it's like free. So we can do something like 1 over x. I don't like that, so what I will do is I will do 1 over absolute value of x. Absolute value of x. What the fuck? 1 over absolute value of x. So that it goes, it's not negative, right? It just goes all the way positive. And here I have, of course, a pole at x, right? Kind of the pole at x, at 0. And you might wonder, cool, maybe this I just divide by 0 once if you want. And here I divide by 0 twice. So the blue one, 1 over x squared. And this is clearly, well, going faster to infinity, right? So it's kind of the measurement of how often we divide by 0. It's kind of the order of the pole. I could now divide by 1 over x cubed or something. No, I don't like that one. Okay, let me divide by 1 over x to the 4. And it just goes all the way up. And even faster to infinity, right? And we just measure how often, how often we divide by 0. No? So 1 over x to the k, and we just say it has a pole of order minus k. Fine. And x to the k has a 0 of order k at 0. So we have just the order of measurement, whether it's a pole or not, is just an integer. No? So minus the negative ones are the poles, the positive ones are the zeros. Okay, so it seems reasonable. And the fun is, this is already very tropical. Yeah? Poles are very tropical. Why? Well, let's have a look. So usually people write this V for valuation of something, and it's the order of a pole or 0 of f. Yeah? Let's say just we do everything around 0. You can shift everything if you want to your favorite point, but let's just stay around 0. And it's actually really easy to see that addition becomes min, which is exactly our tropical addition. It's not quite true, there's a bigger or lower equal, but it doesn't really matter. So the valuation of f plus g is bigger or equal than the minimum of the valuation of f and g. That's exactly what our tropical addition does, right? It turns addition into min. Yeah, and here's just the example. So 1 over x squared is negative 2, as I said. And if you add both up, they also have exponent negative 2. So that's what it is. Both of the evaluation. And you can literally see that here in my little picture, which I, of course, created with the other one. So the red one is 1 over x. Doesn't go to infinity very fast. The blue one is 1 over x squared. It's a bit faster. The green one is a sum. And the green one and the blue one essentially go at the same rate to infinity. That's what this exponent here is measuring. This number here is measuring how fast they go to infinity, if you want. And tropical multiplication is also built in, because multiplication becomes addition. So the valuation of f times g is just f valuation of f plus valuation of g. And again, very easy. If you take the red one and you take it twice, you just get the blue one. So minus 1 plus minus 1 is minus 2. Right? So poles and zeros already have the behavior of what our tropical addition and multiplication, which gives a hint why they should be important, right? They behave a little bit like logarithms. So multiplication becomes addition, simply because you look at the exponent of vanishing, right? So that's very tropical, and will play an important role in tropical geometry. Here's the formal definition. So we use some field, and I tell you one interesting field in a second. So usually we have something like rational functions, or something like that. And evaluation is just a map to R including infinity, and yeah, so the valuation should be infinity if and only if my function is 0. Well, 0 is kind of strange. It somehow vanishes to an infinite order. Anyway. And it should remind you of our favorite kind of object for tropical geometry, right? So evaluation on some field. And then it satisfies the other two rules that we had seen before, right? The multiplication is turned into addition, and addition is turned into min. Up to this little whatever, but it doesn't really matter. And a very tropical example is like rational functions, like in all of the previous pictures that you've seen in this video, and it's just the order of the zero or the pole. The valuation originally comes from, I think, this example, but nobody really wrote it down. People realized a bit later that something like the p-adic integers, where you look at the order, or the valuation would count the number of, so how often p divides your number, and you get those p-adic numbers, which is not something we really do in tropical geometry, but that's, well, you could, but that's where the valuation comes from. But the really example that I would like you to keep in mind is exactly what we discussed in this video. And kind of a standard field people use in tropical geometry is the following. So a power series is just something of the form a0 plus a1x plus a2x squared, and so on and so on and so on. Yeah. Not necessarily finite, just a power series. Just think of it as a formal expression. And this funny symbol that people use here is like this generalization, but now we're allowing essentially rational exponents in the power series. Let me just open my favorite book on tropical geometry, the one we are following here. So we're on page 5.9, and just pull it up again. So page 5.9. And here's an example of such a sequence, right? So you can have something like -3, -2. You can have something like that. So sequences of that form. The notation is usually this funny symbol here. And this is what people often use in tropical geometry. And the kind of fun is that thing is an algebraically closed field of characteristic 0. That's why people use it, I guess. It's like the algebraic closure of the power series. And the valuation on that thing is really just looking at the order of the pole, which in this case is just really the lowest exponent that appears in the series, right? There's maybe some lowest exponent, whatever. Let's have a look at the examples again here. So here the lowest exponent is -3, so the valuation is -3. Here the lowest exponent is 2, so the valuation is 2. So not very, very, very easy idea, but very useful, and behaves like a logarithm, so behaves like something very tropical. Anyway, I hope you enjoyed this video, and I also hope to see you next time.